Terminal voltage, or the actual voltage you get from a battery. Okay? What's printed on that battery, Gabor? How many volts? It's printed on there somewhere.
1.5.
1.5 volts. You were away yesterday. We noticed all batteries, all the small ones, they're all 1.5 volts. We said it's because it's the same chemical reaction going on in each of them. Larger batteries have more charge, and so they'll last longer. But if you were to hook that battery up in a circuit, you would find you don't get 1.5 volts. And the reason is batteries themselves aren't perfect. They have their own resistance inside, an internal resistor. You lose a little bit just traveling through the battery. So what's terminal voltage? It's the actual voltage between the ends of a battery or cell. The ends or posts of a battery are called terminals. A cell itself contributes some resistance. In other words, if you want me to draw a battery properly, I should have a little tiny internal resistor right there. We often use a lowercase r because we don't want that internal resistance to be so big that we lose all of our energy traveling through the battery. We don't want the battery to heat up. But we do lose a little bit. So when you hook up a 1.5 volt battery, if you actually measure what you're getting, you might be only getting 1.3 or 1.2 or 1.1. It depends. And the question is, what does it depend on? So the first issue we're going to talk about is that all batteries have an internal resistance. Now, sometimes I've been ignoring it. In other words, on all the previous questions that I've been doing with you, when you see this, you can assume I'm giving you the terminal voltage there. You can assume I'm giving you the terminal voltage there. You can assume I'm giving you the terminal voltage there. But now we're going to be a bit fussier. Oh, wrong block, Mr. Duke. Now we're going to be a bit fussier. So here is our equivalent circuit. What you'll often see to let you know that it's an internal resistor is they'll have the battery like this, and they'll often draw a little dotted box around there to suggest that's inside the battery. Usually they'll put the internal resistor below the negative. Sometimes they'll flip it. Sometimes they'll have the circuit this way. But you can again still tell that that's meant to be the internal resistor because it's meant to be inside the battery. Don't get out your ultimate review, but I'll show you what I mean on the ultimate review. If I just scroll through here, we're ignoring terminal voltage on that one. In other words, we're pretending that battery has no internal resistor. Oh, there. That's the internal resistor, and we're going to be finding or using the terminal voltage. This battery is rated at 6 volts. You're not going to get 6 volts. So, some terminology. What's printed on the side of the battery is called the EMF. It stands for electromotive force. It's not a force in newtons. It's an archaic term that's left over from when electric vocabulary was being used, but they didn't quite understand what was going on. So this here, symbol, kind of a curly written E, that's printed on the battery. It's the maximum theoretical voltage that you'll get if there was no internal resistance, which you'll never get. I is the current through the cell, little r is the internal resistance of the cell, and V terminal, I'll probably abbreviate it V term, is the actual voltage you're getting once you've hooked this battery up to a circuit. And it changes. But if you want my ski hill analogy, Kai, the internal resistance is kind of like when you get off the chairlift, there's a tiny little hill you ski down to get off of the chairlift. You do lose a tiny bit of height just exiting the chairlift. That's like the little voltage loss that you lose going through the internal resistor. Let's just do one here. Example 1 says, what happens to the cell voltage measured by the voltmeter if we close the switch? This is not yet terminal or voltage, but this is just a thought puzzle. If we close the switch, Well, let's see. Traveling through this battery, we will lose a tiny bit. How much will I lose? I times little r. Which I? Leaving the battery, I total. So put a little I total times little r. That's how many volts we're going to lose. Okay? Let's make up some numbers. Let's suppose this battery has it, don't write this down, just watch, has an EMF of 12 volts. Let's suppose little r is 0.2 ohms. If I total is 1 amp, well, you would have this. Get your calculators out, folks. You'd start out with 12 volts, but you would lose I times little r. You would actually only have, if you measured across the terminal with a voltmeter, you would measure 1.8 volts. What if you hook it up to something where there's a bigger current that requires 2 amps? Now you're only getting actually 11.6 volts out of the battery. You're losing 0.4 traveling through the battery. What if you hook it up to a different resistor, and that resistor requires 3 amps to run? Now you're no longer getting 12 volts. Now you're only getting 11.4 volts out of the battery. You're losing 0.6 traveling through the battery. So, erasing this, here's the real question. If you close this switch, what happens to the total resistance? Gabor. If our total goes down, what happens to the total current? And so this number just got bigger. So you're losing more. I total times R increases. And so the terminal voltage will actually decrease. You'll measure a smaller voltage across the terminals. This is a pretty abstract one. It's going to be easier, I think, if we just dive in with some numbers. Example 2, I like example 2, I like example 2. Looks like downhill is this way. Now, here we didn't do the dotted box. Those dots are meant to be terminals, but it was really hard to get the little dotted box to go, so if you want to, you can do that, or you can just clue in because it said find the terminal voltage, that resistance is meant to be internal. All right, let's ski. Step 1. Label downhill. Did that. Step 2, find total current. Do you see amps anywhere? No. Step 3, do I know 2 things? Do I know 2 things anywhere? Okay. Step 4, ski. How many volts, Danica, am I getting from the battery? How many am I losing through this 2? Don't know. How many am I losing through this 30? Don't know. Skiing doesn't help. Kai, you know what I'm going to do as a last resort because this time I actually have to? I'm going to redraw this. I have 2 resistors in series. That's the same as a single resistor. How big? 32. Is that all right? You know what? I'm going to be lazy, Garrett. I'm not actually going to redraw it. You can if you want to. I'm just going to say this one, I can tell you our total is 32. And I can tell you what our total EMF, I'll put a little EMF, that's V total. I can tell you what's printed on the side of the battery. What's printed on the side of the battery according to this question? So what's the total current that we're going to get going through this circuit? That's going to be V total over R total. It's going to be 20 divided by 32. 0.625 amps. And now I can tell you the terminal voltage. The terminal voltage is that voltage right there. How will I figure it out? Well, how high was the chairlift? How high was the chairlift? What's the EMF? How many volts? Minus, what did I lose coming off the hill? I times little r. That voltage. It's going to be 20 minus 0.625 times 2. 20 minus 0.625 times 2. Even though this battery says 20 volts on the side, that's the EMF, we're actually in this specific circuit only going to get 18.75 volts. We're losing a little bit of voltage traveling through the circuit. Now, Xavier, if I put a different resistor there, instead of 30 ohms, if I put 20 ohms or 40 ohms, this would change. This is where my ski hill analogy breaks down, because in real life, the bump at the end of the chairlift doesn't magically change height depending on what the other hills do. Okay, but the ski hill analogy has carried us pretty good. Not going to complain. So example 3 says, find an expression for the terminal voltage if the cell supplies energy to the circuit. I guess if you want me to find an expression, the terminal voltage is going to be what's printed on the battery minus what you lose going through it. Did I give you that as an equation? I probably didn't. No. They used to put this equation on the provincial formula sheet, and it bugged me because I was always, well, that's just, you're just using Kirchhoff's laws. Of course, the voltage between those two dots is what that minus what you lose. It's got to be that. I like example 4. I like example 4. Example 4 is a nice question. Example 4 says, find the terminal voltage and find the internal resistance. Well, step 1 would be label downhill. Step 2 would be find the total current, 1.5 amps. This question's going to fall apart. Oh, how many amps in this 30 ohm resistor? How many amps going through the internal resistor? What does this want me to find first? I'll put a little part A right there, a little part B right there. Mason, what does this want me to find first? So, don't write this down, look up. The terminal voltage would be 50 minus I times little r, well, minus 1.5 times little r. Why doesn't that help me at all? I don't know little r. I don't know that or that. Wait a minute. How many volts here? Calculate it, please. What? Sharon, how many volts high was the chairlift grand total? How many did I lose skiing? How many volts must I have lost coming off that? What's the terminal voltage? 50 minus 5. In your head, Zach, without a calculator. Oh, Taryn, you know what? I'm noticing another way to find the terminal voltage. It's the sum of all the outer voltages as well. If there was two of them in series, it would be those added together. So another way you can find the terminal voltage, it's what's left over to run everything. And now I can figure out the internal resistance. Resistance is V over I. How many volts are running through, Paige, that internal resistor? How many amps? It's just going to be whatever 5 divided by 1.5 is. This is going to be a repeating decimal. And I get, I guess the internal resistance of this battery is 3.33 ohms. Kevin, I don't know if you remember, I said I'm hopefully not going to be teaching you anything new. We're just being a bit more accurate. So the concept of internal resistance, but have you learned any new Kirchhoff's laws or any new Ohm's laws or anything like that? No. This is a more accurate representation of how circuits work. As soon as you hook a battery up to something, as soon as current starts flowing through the battery, you lose a little bit of voltage to that. How much? Depends what you're hooking it up to. Example 5 says, find the terminal voltage if the cell is being charged. Huh? Oh, I guess we got a 30 volt charger over here. I guess downhill is this way. What's the total voltage in this circuit? Well, how high is the big chairlift? I guess we gain 30, but now we're going backwards through a chairlift, so we lose. You know what the net voltage of this circuit is? It's 21 volts. That's what's left over. What's the total resistance in this circuit? Well, there's 3 resistors, but the nice thing is they are all in parallel. Sorry, wrong word. All in series, which means I can just add them up. It's going to be 5 plus 5 plus 1 in your head, Zach? Okay. Well, what's the total current flowing through this circuit? That's going to be V total divided by R total. It's going to be 21 divided by 11. So I'll write 1.91, but if I need to carry some extra digits, I'll just go 909090. Okay. How many amps? Okay. How many amps are going through the 1 ohm resistor then? How many volts through this through this 1 ohm resistor then? I think also 1.91 volts, because I times R. Okay? Now remember, we're going this way, against the grain. So we're actually skiing up that little hill, getting a little bump, and then going down the chairlift. So what's the terminal voltage here? Instead of losing voltage, here we're going to be gaining voltage. And I could also prove it to you, George, if I put the 1.91 amps there and there, found those voltages, subtracted 30, you would find you had 10.91 volts over here. How many volts is the battery originally? How many volts are we measuring across it? That extra 1.91, that's what's recharging the battery. This is why it takes a long time to recharge batteries. How could I make this number bigger? Well, I could make this resistor larger, but then when I actually use the battery to run something, I'll be losing so much going through that internal resistor that doesn't help. So we can't have it both ways. We can have a tiny internal resistor that's going to allow us to use most of our voltage to run a device, But then if we want to recharge it, it's that tiny internal resistor that gives us that tiny difference in voltage. That's what's doing the recharging. It's going to take a while. Or we could have a really, really big internal resistor. But then, when you plug this into another device, you'll have a terminal voltage instead of 9 volts of like 2 volts. You might lose 7 volts going through the battery, and you only have 2 volts, 2 joules per coulomb left to run the device. Doesn't do any good. Now, there's all sorts of clever workarounds that we're trying to figure out, but this is the basic issue with basic recharging of batteries. You want a battery that will power a lot of devices? It's got to charge up pretty slowly because you want a small internal resistor. You want a battery that charges up really quick? It's not going to be able to run much because you're losing almost all your energy just traveling through the battery. Mr. Dewitt, how do quick charge? I don't know if for quick charging mechanisms, do they have a separate resistor in the battery that's larger that the battery only follows when you're recharging? I don't know. I haven't dove into how all that works. But that's the tug of war conundrum we have. So this says, find an expression for terminal voltage when it's being charged. The terminal voltage would be the EMF plus I times little r. In your homework today, there is going to be some recharging of batteries. On the ultimate review, there is going to be, I think there's one question where you are recharging batteries. There's a couple of questions where there is more than one battery. On your test, I will not give you any of that. You will have only one battery and they will not be recharging. Terminal voltage is fair game, but it'll just be one battery. So in summary, turn the page. If the cell is supplying energy to the circuit, well, it's what's printed on the side of the battery minus what you lose traveling through the battery, which is really Kirchhoff's laws and Ohm's laws in disguise. If we're recharging the battery, it's what's printed on the side of the battery plus what you gain going through the battery, because you're going backwards through the battery. And again, I can gain faster by making this bigger, but then when I plug it in over here, I'll be losing a lot more going through the battery. So, Mr. Dewitt, if we wanted to write this as a single equation, this is what they used to give you on the provincial exam. I just found that so unnecessary because I think we can solve these using Kirchhoff's laws. And you know me enough to know if I can do something without needing an extra equation, why burden myself with extra stuff? What's your homework? Number 1 is good. 2 is good. For number 2, I would dulp. 3 is good. 4 is good. Skip 5, skip 6. 7 is good. Skip 8. 9, or as I like to say, 9. 10 is good. 11 is good. But we'll skip 12. Folks, that's the unit. I've thrown a lot at you. You need to practice this. So tomorrow is going to be a work period. What's the block order tomorrow? Okay, so I see you after lunch. Don't be late. You got a take-home quiz, but it's going to be work on the ultimate review, work on all the homework. And this is also your chance to ask me some of the nasty questions from the homework, both tomorrow and Monday. There are some really nasty ones, especially from yesterday's lesson, that I fully expect kids to be asking me about, but I want to give you a chance to maybe have that aha moment yourself.